start with the first term projects. Indeed, this is also the best project. We selected 5 projects for today. We tried to keep from different fields among the good ones, but the specific one is really the best project. Also, it's they work with Mitiq, what Sarah already mentioned, the project supported, developed under Unitary Found. So Amir and Tuğba, also 2 successful students of QCourse511, they will present it. So I think we will start with Amir.
Great. So yeah, we're going to present about benchmarking error mitigation techniques. Our project we had 5 members on our team: myself, Mandi, Renendu, Samya, and Tuğba, who's also going to present part of this. So why are we interested in error mitigation? Well, we're dealing with noisy quantum computers, and until we have fault-tolerant quantum computation, we need to do something about that to get useful results. Quantum error correction has been around for quite a while. It is a long-term solution. So that's why quantum error mitigation is interesting to us in the near term. It requires less resources, from qubit counts in some cases, and has shown to have good results with some of the work that's already been done. So we focused on using Mitiq, the Python toolkit, which was mentioned. It's a unitary fun project, and it was awesome to work with. It implements many of the techniques that we were interested in learning about from the literature. And we primarily were wanting to look at how different noise models stack up against these different techniques. We chose as our benchmarking circuit quantum phase estimation, since that is a important or deemed important circuit or algorithm. And so let's start with Neuro Zero Noise extrapolation. So the way this error mitigation technique works is the point is to increase noise scaling in a circuit so that you can extrapolate from that and predict what expectation value should be for the evaluation of the circuit. And you do that by folding the circuit. And folding is there are different ways of folding, but essentially you're duplicating the circuit many times where the duplicates are equivalent to identity operations. So you're not modifying the outcome of the circuit other than to increase the noise. And some of the advantages to this are that it's a simple framework to implement. It can be applied without knowing the characteristics of your hardware, so tomography is not needed. And it requires, some of the limitations are that it requires circuits of low depth because you're doing this folding. So as you may know, our quantum hardware has T1 times that are not the longest. So if you increase the depth of your circuit, well, there may be practical issues with what is even possible to execute within that time. Also, the choice of ansatz for extrapolation is not necessarily known. So there are different options there. When you use this in Mitiq, you can tweak what form of extrapolation you want to use. Next, we have probabilistic error cancellation. And this is using the noisy gates that exist in the quantum hardware and creating essentially quasi-probabilities of these operators to form a perfect gate. And you sample the circuit many times. And through this cancellation of these these noisy gates can essentially cancel some of the noise in the system. There's another paper that talks about the fundamental limits of error mitigation, and PEC is put forward as this near optimal technique. The unfortunate part is when we actually worked with this, we found that it really only works for low depth circuits because the scaling of the samples grows significantly, as you can see on the left graph, as you increase the depth. So the advantages are it doesn't require noise scaling, so you're not actually increasing the length of the circuit by much. And the limitations are that it does require gate tomography. So you need to know the characteristics of your hardware in order to generate these ideal gates. And as I mentioned, the overhead increases exponentially with the number of gates. So next, Clifford-data regression. This is an approach where you take your circuit and you generate a near Clifford circuit. Why near Clifford? Well, Clifford circuits are simulable on classical hardware with only polynomial overhead. So the idea here is you generate a circuit that's very close to the circuit you want it to run. You run it on classical hardware, you run it on the noisy hardware, you generate a lot of training data, and then it becomes a regression problem. There are now variants of this that make use of zero noise extrapolation and CDR that are in the literature. Advantages are that it scales. It's also a self-tuning technique, so no tomography is needed. But it does require a potentially large number of shots for this training. So I'm going to hand it over now to Tuğba.
So the error mitigation techniques that we have mentioned so far were the ones that have already been implemented in Mitiq. So we also investigated other quantum error mitigation techniques in the literature, and randomized compiling is one of them. Next slide, please. Before going into the details, let's first talk a bit about the noise and errors. The main source of noise in quantum circuits is gate errors, which can be classified in two groups: incoherent errors, which are easy to handle, and coherent errors, which are hard to handle because they occur due to some small miscalibrations in the control parameters, and so produce similar errors in consecutive executions of the circuit. By this way, they preserve state purity, and this can lead to some bias after consecutive executions. To circumvent this issue, we can use randomized compiling to convert coherent errors into easier to handle incoherent errors by adding some randomizing gates in front of and after the CNOT gates, which are the main source of the noise in the circuit. These randomized gates are chosen not randomly. They are chosen such that the overall effect of the CNOT gate and so the circuit doesn't change. By this way, if we first obtain a target circuit, which is an equivalent version of the original circuit, and an estimation circuit, which is created by first deleting all the single qubit gates of the original circuit and then applying randomized compiling. In this estimation version, we know the output of the circuit, since these deliberately chosen randomizing single qubit gates do not alter the initial state at all. And so after measuring the observable, we can use this measurement to scale the result of the target circuit and obtain a better expectation result. Next slide, please. This technique can be used in combination with the other techniques: zero noise extrapolation, probabilistic error cancellation, and Clifford-data regression. We also benchmarked the performance of randomized compiling with our QPS circuit, and we obtained error performance results and show that, yeah, randomized compiling brings error performance improvements. Next, please. So to conclude, we can say that in this quantum era, NISQ era, it is crucial to mitigate errors to obtain reliable results. Quantum error mitigation has arisen as a collection of techniques that are more practical than quantum error correction solutions, as they offer low overhead methods to estimate the results, that is the observable values, I mean. We realize that the choice of the techniques seems to have the need to be custom tailored to the specific problem, as none of the techniques seems to be the best in all cases. We had concerns about selection of the benchmarking circuit, depth of the circuit, observables, number of shots, and number of runs to obtain smoother curves through averaging. Simulations were time costly, usually requiring multiple hours to complete for iteration. Considering that the project was only a month's time, we believe that our outcomes were overall satisfactory. Amir has the intention to add without noise, and I have the intention to add randomized compiling to Mitiq. So we conclude that quantum error mitigation is a very fertile area for future research and seems to be so for the years to come. So this concludes our presentation.
Thank you very much. Is there any question? You can raise your hands or write in the chat. So as far as I understand, you plan to continue?
Yeah.
As a group or subset of group?
Yeah, we were speaking this issue with Amir.
Okay, I think Sarah has a question. Please.
Yeah, I was going to ask, you said that the simulations were very time costly. What simulators were you using out of curiosity?
Oh, good question. We were using the Qiskit. No, sorry, we ended up using Cirq because of how Mitiq seems to rely on it as well.
Yeah. No, that makes sense. There might be other types of other simulators you could try or we could help you with that might be a little bit faster or at least offer different sorts, because I know the noise models that the Cirq one can support is not fully expansive. So I guess that's my other question, is other noise models of interest to you?
Yeah, we ran into a problem where for Z&E, we were able to test on all noise models, but with the other techniques, we were limited in what was supported. Yeah.
Regardless, great project, guys.
Thank you. It was great working with. Oh, sorry. Go ahead.
Oh. I was just gonna say, you should certainly we'll share the recordings at the Mitiq community calls, but if you guys want to, please feel free. We can add you to the agenda to give just even say briefly like about the conclusion slide, because we were talking about roadmap planning for some of those other mitigation techniques.
Thanks. Yeah, it was great working with the team and getting support throughout the project.
So Amir and Tuğba, are you planning to apply for a micro grant based on your work? Have you thought about it?
No plans on my end.
I offered Amir to continue with the second part of the project a minute ago. Okay. I mean, it sounds great. I hope you can continue. Okay, probably it can be publishable also. Yes, I mean, you can. Do you consider already to submit somewhere, or you haven't considered?
You mean for the work we already did?
Yeah, I mean, or a little further, I think more, and then submit somewhere.
Yeah, I think there's more work to do. This is more of I think a review of the current work. There are plenty of areas to explore, though. That might be fun to do a future research project.
Okay. Okay. Any other question? Okay. I would like to thanks to your group and also both of you. Yeah, Sarah also encouraging you for publication. So it looks like you can go many directions from this project. Of course, it should also fit your agenda. Maybe you are already busy with some other projects, I don't know. But I think, yeah, you can continue. Thank you for both of you.